So we now start solving the problems of this section. Exercises 5.3. In the first one, we have to use Fermat's theorem to show that the prime 17 divides this number 11 to the power 104 plus 1. So we will immediately apply Fermat's theorem with the prime 17. Since (11) and 17 are distinct primes, so they are also relatively prime. It follows from Fermat's theorem that 11 to the power 16 is congruent to 1 modulo 17. The exponent here is 1 less than the modulus. So, now what we do, we raise both sides of this congruence to their 6th power. This we can do because it's one of the things we can do to a congruence. Or, so this becomes 96 is congruent to 1 mod 17. But that's not 104, that is 96. So we need 8 more 11s. And for that we have to now calculate separately. We of course have this. Actually they are equal, so also congruent. Now this is just the 4th power of 121. Instead of writing the modulus, we keep on writing the congruent sign. We can do this, okay. This is an accepted way of writing congruences. You combine many congruences and write them at once. And ultimately, when you finish, there you write the modulus, mod 17. It's like writing a series of ordinary equations. Okay, now we need to figure out to what number 121 is congruent to modulo 17. In other words, we have to divide 121 by 17 and see what the remainder is. It turns out that the remainder is 2. In fact, if you multiply 17 and 7, what do you get? 119. That is 2 less than 121. So the remainder is 2. 16 and 16 is congruent to minus 1 modulo 17. So now what we can do, we can multiply these two congruences, this one and this one. Hence, to the power 104 is congruent to this, which is congruent to 1 times minus 1, which is congruent to minus 1 mod 17. Now just translate this congruence in the language of divisibility. That is 17 divides this plus 1. So that's the solution. Next, number 2. In 2 there are 3 parts, A, B and C. So instead of taking down the entire question at once, what I will do, I will first take down part A, solve it, and then I will take down part B, solve it. Like that we will go. So let's see part A first. If A is some integer, GCD of A and 35 is 1, show that A to the power 12 is congruent to 1 modulo 35. Here also we will have to use Fermat's theorem, but we cannot do it to 35 itself because it is not prime. It is, however, 5 times 7 which are primes. In the beginning we note this, since A and 35 are relatively prime, so A and 5 must also be relatively prime, and A and 7 must also be relatively prime. Because if not, say A and 5 are not relatively prime, then 5 being a prime would imply that 5 divides A. But if 5 divides A, then 5 becomes a common divisor of A and 35, which is already greater than 1. So how can the greatest common divisor be 1? That is why. So by Fermat's theorem, the congruence we will get for 5 is this: A to the power 4 is congruent to 1 modulo 5, and we get 1 for 7 as well. A to the power 6 is congruent to 1 modulo 7. Hence, so how do you get 12 from here? Just take the third power of both sides. Mod 5, and here you take squares on both sides. Thus, since 5 and 7 are relatively prime, we have A to the power 12 congruent to 1 modulo 35. This is one of the properties of congruences. If the moduli are relatively prime, then you can take their product. If the other things are the same, A to the power 12 on one side and 1 on the other side. If you have forgotten this property, let us also see why this is true. This is the end of the solution to part A. Okay, but let's see why this last line is true. If we express these congruences that we considered here to get this one as divisibility relations, we are going to get this. The first one tells us that 5 is, this one. 5 divides a to the power 12 minus 1. And the second one tells us that 7 divides a to the power 12 minus 1. And then a corollary to Euclid's lemma tells us that since 5 and 7 are relatively prime, their product will also divide the same number, which is just 35. And that, when you just write in term as a congruence, is this. That's how. Okay, so this is part A. Next, part B. If GCD of A and 42 is 1, show that $168, which is 3 times 7 times 8, divides what? A to the power 6 minus 1. Alright. We are able to apply Fermat's theorem again, and we will do with the primes 3 and 7. But we will have to do something else for the factor 8 because it's not prime. Well, you can consider modulo 2, but that won't really give you modulo 8. So something else needs to be done here. But let us first see what we can do with 3 and 7. Since GCD of A and 42 is 1, we have okay, now what type of number is 42? If you factorize 42, you get 2 times 21, that means 2 times 3 times 7. So A is relatively prime to 42 means A is relatively prime to 2 and 3 and 7. So GCD of A and 3 is 1 and GCD of A and 7 is also 1. And being relatively prime to 2 means what? It means being odd. And A is odd. Okay. So, by Fermat's theorem, we immediately get two congruences. The first one for the prime 3 is this. A square is congruent to 1 mod 3. And the second one for the prime 7 is this. This is congruent to 1 mod 7. The thing that we want to show that this divides A to the power 6 minus 1. For the prime 7 at least, we have already got it in the final form because 7 divides A to the power 6 minus 1. But this one we have to change a little. That is, A to the power 6 is just this, which is congruent to 1 cube, which is congruent to 1 modulo 3. Alright, now what do we do about 8? About 8, let us have a little discussion first. And from that discussion something will come out and then we will continue the solution with that thing. You know that the division algorithm gives us this fact, that each integer is in exactly one of these 8 forms. Either it looks like 8k or 8k plus 1 or 8k plus 2 or 3, 4, 5, 6 or 7, depending on what remainder is left when you divide that number by 8. Here, for example, the remainder left is 0, or in other words, all the numbers that are divisible by 8 look like this. Those that leave remainder 1 look like this, and so on. Now, we want to know what type of number A is. It is given that A is odd. So from these forms, we can already rule out those that are even. That means A cannot be of this form. A can't be 8k plus 2 or 8k plus 4 or 8k plus 6. So it can still be one of these 4 remaining forms. If A looks like this, then A is congruent to 1 modulo 8. If A is of this form, it is congruent to 3 modulo 8. This form of numbers are congruent to 5 modulo 8, and these numbers are congruent to 7 modulo 8. This is our discussion. So that means we can now write this. Let me continue from here itself. Now, since A is odd, we won't write all these things. Okay, we are straight away going to write what we are getting here. So A is either congruent to 1 mod 8. Fermat's theorem will give you only the modulus 2, not the composite modulus 8. That is why. Or A is congruent to 3 mod 8, or A is congruent to 5 mod 8, or A is congruent to 7 mod 8. Now we have to see what happens to the 6th power of A in each of these 4 cases. That may seem like a lot of calculation, but you will see that it's actually nothing. If, in fact, the first one is immediate. If A is congruent to 1 mod 8, then A to the power 6 is also congruent to 1 mod 8. So whatever we are seeking is really just there if A is congruent to 1 mod 8. But what about the other cases? Now we will see. If A is congruent to 3 mod 8, then A to the power 6 is congruent to 3 to the power 6. Now 3 to the power 6 may seem like a large number. I mean, you have to think a little for this. But note that this is also 3 square whole cube. That means 9 cube. And 9 is congruent to 1 mod 8. So again we are getting 1. Next comes this case. If A is congruent to 5 mod 8, then 5 to the power 6, which however is the cube of 25. Now note that 25 is also congruent to 1 mod 8, because 25 is 3 times 8 plus 1. The remainder when you divide 25 by 8 is 1. And for the last one, you don't even have to consider the sixth power of 7. If A is congruent to 7 mod 8, then luckily A is also congruent to minus 1 mod 8. And so A to the power 6 is congruent to this, which is again 1. Thus, in general, no matter what A is, we are consistently getting this congruence. So this was the remaining congruence that we wanted, and now we have this. Since 3, 7 and 8 are pairwise relatively prime, we thus have this, where we take their product as the modulus, and that is our this thing 168. Yeah. That is (168) divides A to the power 6 minus 1. This is what we wanted to show. And then, so this is the solution to part B, and then there is a part C also. If A and 133 are relatively prime, and so are, there is another number, B and 133. Then show that (133) divides the difference of their 18th powers. Okay. Let us first see what type of number this one is. Note that 133 is 7 times 19. Let me just tell you something about this notation dot. I have said this before many times, but again I am going to repeat. When you want to write dot to denote multiplication, write it in the middle, not at the bottom. If you write it at the bottom, it means the decimal point. But if you write it here, then it means the multiplication as an operation. Okay. Since A and 133 and B and 133 are relatively prime, we have, let me also see if I got the numbers correct. Yes, okay. So we are now going to have, because of these things, these as well. A and 7 are relatively prime, and so are B and 7. Similarly, A and 19 are relatively prime, and so are B and 19. So by Fermat's theorem, actually we are going to apply Fermat's theorem with the prime 7 and 19, of course, but to both the numbers A and B. So let me write all the congruences, let me combine them and write like this. For the prime 7, we are getting a to the power 6 is congruent to 1 modulo 7, but that is also congruent to b to the power 6. And for the prime 19, we get the most favorable numbers, because here we are getting the 18th power just from Fermat's theorem. That is, oh, why am I again writing this? Okay, I can straight away write this, which is congruent to this modulo 7, and so just like the other cases, this will be congruent to b to the power 18, and now the modulus is the product of 7 and 19, that is 133, i.e. 133 divides this difference. That's what we wanted to show. So that is part C. Let us do one more. Number 3. From Fermat's theorem, deduce that for any integer, non-negative integer, something happens. Um, 13 divides 11 to the power 12n plus 6 plus 1. You can actually, in fact, we have come across this type of divisibility relations, and we proved them by using mathematical induction and elementary divisibility, primes, those things. But now Fermat's theorem allows us to do this at once without relying on induction. Since GCD of 11 and 13 is 1, it follows from Fermat's theorem that, let us straight away consider this power 12n plus 6. So this is congruent to 11 to the power 12 to the power n times 11 to the power 6. This is where we use Fermat's theorem, because 11 to the power 12 is congruent to 1 modulo. We haven't written modulus, but that is 13, you understand. 1 to the power n times 11 to the power 6. So this is 11 to the power 6. So you now have to deal with only this number. And this is 11 square whole cube, that is 121 cube. Now if we divide this number by 13, what remainder do we get? The remainder that we get actually is 4. Why? Because 13 times 9 is what? 117. 18, 19, 20, 21. Yes. So this is congruent to 4. That means the cube is congruent to 4 cube. And 4 cube is 64. Now 5 times 13 is 65. That means 64 is congruent to, 65 is divisible by 13. So 64 is congruent to -1. And finally we write the modulus. So this plus 1 is divisible by 30. If you are writing this on exam paper, however, you should not hurriedly do it like this. You should at least write that it follows from Fermat's theorem that 11 to the power 12 is congruent to 1 modulo 13. Hence we have this. Okay, so that's just it. So let me end the video here itself for tonight. Tomorrow again we have our upload, and tomorrow let's go back to topology again. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.